Hi everyone, welcome back. So now, we stop at we have done the temperature scale. At the same time, how we mention all the types of thermometer that we have clinical thermometer, resistance thermometer, and so on. Then we check a look at the calculation that involved that when we have upper fixed point and when we have lower fixed point, and we talk about linear expansivity as well, together with volume expansivity and at the same time the cubic expansivity. So please, if you check material, you see many examples concerning that. So now, lastly, let's talk about heat capacity. General physics. So we continue from where we stopped. We're talking about heat capacity and specific heat capacity. So now this will be based on today's discussion, so that we can round up the one we have for the heat and temperature. So so two cases, we have heat capacity and we at the same time we have specific capacity, which is defined as the heat required to raise the temperature of a substance by 1 degree Celsius. You see, every quantity that we have in this world, either being a body or being an object, either be living or not living, it has its own specific heat capacity. For example, you cannot compare the rate of how, for example, if you're inside the sun, let's say we are inside the sun now, let's say a person that wear either black coat, or let's say a black clothes, and the other one wear the other color, let's say white. You can see, the rate of comparing their radiation will be somehow different. So every quantity that we have its own specific heat capacity and heat capacity as well. So heat capacity, but in our material we define it so that you know the difference between the two. So heat capacity, it is denoted by C. That one is given as heat capacity, which is H rather. It's nothing but joule per Kelvin, or let's say joule per degree Celsius, or we can have it as a joule per Kelvin. We said temperature have two things, two units to be precise. It can be measured in either degree Celsius or it can be measured in Kelvin. So either we have it as joule per Kelvin or we can have it as joule per degree Celsius. So it depends on what we have in that particular problem. So those are the things we are going to talk about. So the other one we have is a specific heat capacity, as I mentioned earlier. So here I will define the two terms in the material. So please, in case if you need all those one, just try to subscribe and likes and also share the video. So I will just based on the main thing, the calculation aspect, to save our time. So in this case, if you see H here, in some material they use H or some use a Q. We call it a heat, quantity of heat required. This is a quantity of heat. So, and it's measured in what? It is a form of energy. Since it is a form of energy, it's measured in joule. Good. So it's measured in joules. Then we will be mentioning M here, the mass of the substance. Mass of the substance. And mass is of two forms, either gram or kilogram. So mass too can be either gram or kilogram, either mass of the substance, of object or body. Then the other one we have is a change in theta. This is nothing but a change in temperature. We mentioned that one when we are talking about a linear expansivity, right? Under expansion, change in temperature. So if you are given two temperature here too, the convection doesn't matter. Either the value is in degrees Celsius or is in Kelvin. You can use any of this. Then the other one we have is C, which is nothing but specific heat capacity. Specific heat capacity. Everybody we have or object have its own specific capacity. So now, therefore, we have the equation to be this. So don't forget, I will define all this one to save our time, since we only want to base on only calculation aspect. So heat is equal to MC change in theta. We have already explained all the time, one after the other. We say heat as a quantity of heat, which is measured in joules. Temperature too can either be degrees Celsius or Kelvin. So that means the only one I want to derive with the formula is for C. So let's derive the formula for C. The unit. So if I make the C and the subject here, divide both side by M change in theta, M change in theta. So if this cancel this, I can have C to be 8 divided by M change in theta. And we know that the H is joule, mass is kilogram. At the same time, change in temperature is Kelvin. So that means this one is a joule per kilogram per Kelvin rather. So that is the SI unit of what? SI unit of specific heat capacity. So the formula that we've been targeting here is going to be heat, quantity of heat. You know, I told you in some material they use Q or they use H. So H is equal to MC changing in theta. So these are formula that we're using for this particular case. So you don't need to perplex. The definition of heat capacity and specific capacity, if you check our materials, I will explain them in details, give examples so that you'll be able to understand it more better. So now, in any problem we are solving, you may be asked to find either heat capacity or mass, or to find the C, or to find the value of change in theta. It depends on the problem. So let's see, like I will solve many examples here so that you can be able to understand it more better. Let's look at question 1. Let's look at question 1. So let me write the formula here. We have heat is equal to MC change in theta. So let's look at this question 1. They said, what is the quantity of heat? What is the quantity? What is the quantity of heat that will be given out? That will be given out if a brass of mass, let's say 350 gram, is cooled from 95 degrees Celsius to 20 degrees Celsius, taking specific capacity of brass to be 380 joule per kilogram per Kelvin. So this is the first examples. So let's see how we are going to tackle that. They said, what is the quantity of heat? Hold on, sir. So we are given that. They said, what is the quantity of heat? So we are asked to find the heat that will be given out if a bra of mass 350 gram. You know, I told you in physics what matter most is you firstly write out the given data. So the mass we are given here is 350 gram, but you can see the value is in gram, and we need to convert it to kilogram. So please, you know, I've mentioned how to conversion of quantities. So now this is gram. I can convert it to kilogram, divide the value by 1000. So if you divide this, I think we are going to have 0.35 kilogram. Now, they now said it's cooled from 95 degrees Celsius to 20 degrees Celsius. That means here we are given two temperatures. I can find the change in theta here to be 95 minus 20. So if I do that, here we are going to have 75 degrees Celsius. So I told you here, the conversion doesn't matter. Now, calculator. So taking the specific capacity of this one to be 380. So given that our C is equal to 380 joule per kilogram per Kelvin. So now you can just apply the formula. Using the formula, heat is equal to MC change in theta. So now we have the mass, we have the value of C, and we have the value of change in temperature. So here I can have this one to be heat is equal to, our mass here is given as 0.35 multiplied by our C that we have from here is 380 multiplied by our change in temperature that we are given there is 75. So now let's take the values and multiply the three values that we have there. 0.35, 380, 75. So if you multiply that one together, what you have here is 9975 joules. So you can see that it's straightforward. And let's see another examples. see another one. So let's see another examples and see how we are going to. They say calculate the final temperature. Calculate the final temperature of 2 kilograms of alcohol at 25 degrees Celsius when 20160 joules of heat energy is added to it. And they said take specific heat capacity of alcohol to be 2520 joule per kilogram per Kelvin. So now, these are another questions. Now, they said calculate the final temperature. You know, normally, let's first look at the given data. That's very important. The given data, the data given from the problem. So we asked to find the final temperature. You know, normally, I used to tell you that if you are given to temperature, we know that changing temperature should be temperature 2 minus temperature 1. So meaning the one, this is the final, and this is the initial. So from the problem, they said we should find the final temperature, meaning we are looking for the final temperature of 2 kilograms of alcohol. You know, when the value have kilogram is over into what? Yeah, good, mass. So our mass here is given as a 2 kilogram, and you can see the values in kilogram. Do we need to convert this one again? Yeah, now fine. Since the value is in kilogram, so at 25 degrees Celsius, so our temperature one we have here is 25 degrees Celsius. So when 20,160 joule of heat, so our heat we have here is 20,160 joules. So we are given the specific capacity to be 2520 joule per kilogram per Kelvin. Now, so since we have the formula, from the formula that we have, we know that heat is equal to mc change in theta. So now I'm looking for the final temperature. I can have this to be heat is equal to mc, that is at temperature 2 minus temperature 1. So now the value of heat given to us is given as a 20160 equal to our mass that we are given here is 2 kilograms multiplied by our C that we have here is 2520. Then brackets I'm looking for temperature 2 minus our temperature 1 we have here is 25. You can see we just make a simple substitution. The value of our heat given to us is 20160. From the data given, our mass is 2 kilograms. We have 2 kilograms here, and we are given C that C is 2520. Then we have to find the final temperature. The minus the initial temperature that we have is 25 degrees Celsius. So here, the conversion doesn't require here. You don't need to convert your temperature. Either you are given the value in Celsius or the value in Kelvin. You can just use any of the two. So now, so here we can have this to be 20160 is equal to 2 multiplied by this. I think we are going to have 5040 theta 2 minus 25. So since what I'm looking for here, you can do it in two ways. If you like, open the bracket with this, or if you like, firstly, redo this one by dividing all through by 5040, 5040. So if this cancel this, I will have temperature 2 minus 25 is equal to, now 20160 divided by 5040. If you do that, we are going to have 4 as our result. That is 20160 divided by 5040. The answer should be 4. So now, since I'm looking for theta 2, I can make my theta 2 as the subject of the formula. If I call it like times, I can have temperature 2 here is equal to 4. So this is minus. When the minus comes here, it's going to become positive. That's going to be 25. So here we have temperature 2 equal to 4 plus 25, we are going to have 29 degrees Celsius. So it depends on what you're asked to find. If you're asked to find the mass, you just have to make that mass at the subject of the formula. So, or if you're asked to find any of these, either mass, you just make your mass at the subject, or you may be asked to find the specific heat capacity. So it depends on the one you are asked to calculate. So let's see if I can see one that will require for us to find. Okay, let's look at this. Then we round it up and move further. So let's look at another problem. Let's look at this. The temperature of a piece of a metal of a piece of a metal of mass 9 gram is raised from 10 degrees Celsius to 110 degrees Celsius when it absorbed 108 joule of heat energy. Determine the specific heat capacity. So this is another problem. Let's see how we are going to tackle that. The temperature of a piece of a metal of mass 9 gram. So let's first look at the data we are given from the problem. So we are given the mass to be 9 gram. But I told you, if you are given mass in gram, you have to convert the mass to kilogram. So if you divide this value by 1000 now, so here we have the mass here to be 0.009 kilogram. So they say it's raised from 10 degrees Celsius, so our temperature 10 degrees Celsius to 110. That is our temperature 2 is 110 degrees Celsius. They now said when it absorbed 108 joule of heat energy, so our heat energy given there is 108 joules. They now said we should determine the specific heat capacity. So meaning we are asked to find the value of C. So there's nothing to worry about since you have the formula that heat is equal to MC change in theta. So now the value of our heat we are given from the problem is 108. I have 108 is equal to, now the mass we have is 0.009. The reason why we use this, you can see we are given 9 gram, but from the problem the mass is in gram, and whenever we are given the mass in gram, we must convert that mass to kilogram. So now 0.09, I'm looking for C, which is unknown. So I have two temperatures. I can find their difference as 110 minus 10. So here we can have this to be 108 is equal to 0.009 C. So 110 minus 10, of course, we are going to have 100. Now we can have this to be 108 is equal to, now what we have is 0.09 C multiplied by 100. Of course, if you do that, I think we are going to have 0.9 C. So since I'm looking for C, divide both sides by 0.9, divide through by 0.9. So here we are going to have 0.9. So if you do that, what we have here is 120 joule per kilogram per Kelvin. Yeah, if you do that, so that's what we have. So it depends on the problem. You may be asked to find either the heat of the substance or the mass of the substance or the mass of the object, or you may be asked to find specific heat capacity or the change in temperature. So the one where you have to find, you can just make it at the subject of the formula. So another one we have we also have what we call method of mixture. Method of mixture. Method of mixture. Under this case, under the heat capacity, we also have method of mixture. So here is when we have three temperatures, when one substance is losing to the other one. So let me just break it down. So when we are comparing two substances together, the one with higher temperature will lose its own heat constituent to the one that have low temperature. Let's say, for example, let's say we have three buckets. Let's say we have bucket A and we have bucket B. Let's say this one contains cold water. This contains cold water. Let's say it's at let's say 5 degrees Celsius, or let's just say it's at cold water. We have another bucket. Let's say this contains hot water. So now it is very hot, and at the same time it is very cold. Now, for example, let's say during the Harmattan season or during the cold season, I don't want to bath with a cold water, and here the water is too hot. What did I need to do? Yeah, fine. I will add them together. If I combine the two together, you know, of course, we are going to have either a cool or a warm water. That's going to be the final temperatures. So here we can say this one is a temperature of the cold water, and here we are going to have temperature of hot water. Then since this one is the final temperature, we can have temperature of final or warm water. So now, if you ask now, between these three temperatures, which one will have higher temperature? Recall from the definitions that we have heat determine the constituent of temperature, and temperature to also determine that either the heat is much or not. So now, since this one have this one will have a high temperature, so here we can just write mathematically that the hot water temperature of the hot water will be more than the final temperature. At the same time, the final temperature too will be also more than the temperature of the cold water, because the cold water doesn't have a temperature compared to that of the hot water. At the same time, the final temperature. So meaning, so here the hot water is losing its constituent to cold water. So here you can say heat loss by hot water must be equal to heat gain by cold water. So you can see, I want to derive a formula from here. Heat loss by hot water is equal to heat gain by cold water. So now we know in general that heat is equal to MC change in theta, right? So now we are using that expression, heat loss by hot water. I'm denoting this as heat loss by hot water is equal to heat gain by cold water. So now that means I can say mass of hot water, C, or since water is water, we have the same specific capacity. So then temperature of hot water is equal to mass of cold water, C of cold water, then change in temperature of cold water. So from these expressions, we have three temperatures there. We have for the hot, for the cold, at the same time final temperature, and we know that this mathematical, this is what we hold, because temperature of hot water will be more than the final temperature. At the same time, the final temperature too will be more than temperature of the cold water. So here I can have this one to be mass of hot water, C. So instead of writing this, I can have temperature of hot water minus the final temperature. We got this from here. So now equal to mass of cold water, C of cold water, then final minus temperature of cold water. Because here, from this expression, the final temperature, which is warm one, or the final temperature of the water, will be more than the temperature of the cold water. So that's why we have this one to be final temperature minus temperature of cold water. So if you look at this one too, we have temperature of hot water minus final temperature, because the temperature of the hot water will be more than that of a final temperature. So if you are solving a problem in this case, if you are given two, maybe we are comparing two objects, so once you or two substances, just look at the one that have the higher temperature, look at the one that have the lower temperature. So the one with higher temperature will be losing heat to the one with a lower temperature. So now it might not be water, it might be any object, maybe copper and any other object. Just look at this expression. The one that have higher temperature will be losing its own heat constituent to the one with low temperature. So let's take a look at some problem. Let's see some examples and how we're going to use that to solve the problem. Now let's look at it. They said calculate the final temperature. Calculate the final temperature of the mixture of 250 grams of water at 65 degrees Celsius is added to 150 grams of colder water at 5 degrees Celsius. Neglect the heat absorbed by the surrounding, and we have to take specific capacity of water to be 4,200 joule per kilogram then per Kelvin. So let's look at this. In the problem, sometimes they might not specify which one is hot one and which one is cold one, but through the temperature, temperature determines the property of heat. So through the temperature, you will be able to figure out which one is be losing and which one will be gaining between the two. So from the problem, they said we should find the final temperature, that is after the mixture. We should find the final temperature. So let's say we are looking for the final temperature of 250 grams of water at 65 degrees Celsius. So from there, I don't know, is it going to be the one with hot one or the cold one? But if you look at the second data, you can see they even mentioned there, and that one have a temperature of 5. So meaning the one with lower temperature will be gaining, and the one with higher temperature will be losing. So that means the mass of hot water, we have the value to be 250 grams. So when I told you, whenever we are given the value of mass here to be in gram, you must convert that mass to kilogram, and we know 1,000 grams equivalent to 1 kilogram. So since what we have here is gram, that's 250 divided by 1,000. So if you divide this, here we are going to have 0.25 kilogram at 65 degrees Celsius, meaning the temperature of the hot water is 65 degrees Celsius. It's added to 150 grams of cold water. So that means the mass of cold water is given as 150 grams. So now this value is also in gram. We can convert it to kilogram divided by 1,000. So here we are going to have 0.15 kilogram at 5 degrees Celsius. So meaning the temperature of the cold water is 5 degrees Celsius. So here for the temperature, the conversion doesn't matter. Either the value is in Celsius or Kelvin. You can use that one. It's only mass that we need to convert. If you are given your mass in kilogram, you are free to go. But if the value of your mass is in gram, you must convert the mass to kilogram, from gram to kilogram. So we have all the data. So you can just apply the formula. From the formula we say heat loss by hot water must be equal to heat gain by cold water. So now from the formula we do the other time, we say mass of hot water C, temperature of hot water minus final temperature, we have derived this earlier, is equal to mass of cold water C, then final minus temperature of the cold one. So please, in some situation, it might not be only water, it might be other substances apart from water. Just look at the one with higher temperature and the one with lower temperature to compare which one will be losing and which one will be gaining. So from the data we have, the mass of hot water we have here is 0.25. That means that we have 0.25 multiplied by, so our C that we have, C of water is the same, either hot water or cold one. So from the data we are given the value to be 4,200, bracket of the temperature of hot water, we have it to be 65. So I'm looking for the final temperature. I can say let the final temperature, maybe I want it to be X. So let the final temperature to be X. So here I can have minus X is equal to, so mass of cold water, we have it to be, what do we have there? Mass of cold water, we have it to be 0.15. Then this is multiplied by 4,200. So final temperature is what I'm looking for, which is X. Then minus temperature of our cold water, we have it to be 5. So here, let's just multiply these two values together to reduce the value that we have at both right hand side and left hand side. So that is our 0.25 multiplied by 4,200. So if you multiply that, we are going to have 1050 of 65 minus X is equal to, so same thing also can be applicable to this. Multiply this by this, 0.15 multiplied by 4,200. So here, if we do that, we are going to have 630, then X minus 5. So now, the next thing here, if you like, you can reduce this value, or if you like, you can just open the bracket. What we have at the right hand side, at the same time, what we have at the left hand side. So if I do that, so 1050 multiplied by 65. So that one gives us 68250. Then 1050 times X, and we have 1050X is equal to, now for the right hand side now, 630 times X, we are going to have 630X, then 630 multiplied by 5, we are going to have 3150. So you see, we open the bracket for the one we have at the right hand side, at the same time the one we have at the left hand side. So now the next step is to collect the like terms. Those who have X to one side, the one without X to the other side. So now I can have the result here to be 68250. Now this is another number without X. If I collect like terms, and we have plus, what we have there is a 3150, or let me just put it here. So from here, if I collect the like terms, we have 68250. So this is minus. So when the minus comes here, we have plus 3150 is equal to 630X. Then this is minus. So when the minus comes here too, we have plus 1050X. So now let's add the one we have at the right hand side together, then the one we have at the left hand side. 68250. So if you add that one, we are going to have 71400 is equal to 630 plus 1050. We are going to have 1680X. So since what we are looking for is X, then we divide all through by 1680. 1680. So if you divide that, we have 71400 divided by 1680. So our result here gives us a 42.5 degree Celsius. So that's our final temperature, which is a 42.5. So even after this one, we also have another one in which we given anything for power, but I will include that one in our materials. At the same time, we also have latent heat, where we have a latent heat of fusion, of vaporizations, or of ice. So all those ones that we add them to in our material. So that's what we have for this chapter. So thanks for watching. Please don't forget to like our videos and subscribe.